All right. All right. So a lot happened over the weekend, but still, how was the exam? I kind of know how the exam went because we were grading all weekend. And so unless I didn't check it this morning. Are the grades up on Bobby Notes? No. Okay, so they should be up sometime soon. I don't know if it's going to be today or tomorrow, but they should be up sometime soon. So the exam went okay. I didn't hear about any technical issues. There were no technical issues, right? Canvas didn't act up, or nobody got kicked out before they were supposed to. That is good, I guess. Are there any questions about the assignment? So this assignment is interesting because it concerns a data structure that is extremely popular, binary search trees. And so if there was such a thing as my favorite data structure, it would probably be trees. And so that's kind of why I like this assignment. It's a lot of fun to work with. So let me know if you have any questions. Okay. Okay, so I'm going to finish fold R now. We just started talking about fold R last time towards the end of class. So let me quickly write that code and then move on. So what we were trying to do was a general purpose equivalent of the total price method, where you would take in an entire list and you would basically distill it down to one thing. And that's the fold operation. Okay. And so the fold R is basically you're starting to fold from the right-hand side onto the left-hand side. And so you can do so quite easily by saying, well, I'm going to get the value for the rest of the list, and then I'm going to combine that value with whatever I know with this object to produce a new value that I send back to my column. Okay. And so we briefly talked about what we need for this. We need basically an ifunc2 like that. Okay. Now, before we move on, and the assignment kind of reveals this, but Java already has these. Java already has existing interfaces for this, for all the function object interfaces that we saw. What that means is you don't need to define your own interface. You can use what already exists in Java. And so basically the I predicate becomes the predicate interface. Okay. Then your ifunc, which was takes in and it defines a function with one parameter and then a return type. This is basically the function interface. So Java 8 and above. Okay. This is also Java 8 and above. So Java 8 is when Java started adding more support for functional programming. And so that's the version you see, function objects, and then I think Lambda function syntax. It was introduced in 8 and then refined in 9. The I comparator, though, is older. This is not really functional programming related. So the interface here was comparator. This is the one you're using currently in the assignment. Okay, so this already existed in Java. Then we have ifunc, and then finally for the fold we were looking at this one, and the existing Java equivalent is the by function. Okay, I believe they also the name of the method inside is also apply. You have to check on the documentation. I'm 95% sure it's the same. Okay, so having known this existing Java interface, let's quickly write the fold in terms of that. All right, so let me zoom out. Where was I writing all of this? So we had just started writing sort of the signature. So I list was here, cons list was here, and empty list was here. Okay, so I'm going to write the fold R right here. So the fold R is going to have a return type of U. It's going to take two things, a buy function, TUU, combiner, and a base value to start with. Okay, so relating this to the total price method, the base value would be an integer, which is 0, because that's the price you start with. And then the combiner in total price is just arithmetic, adding of two integers. That's the function that will take in two numbers and a number and a book, and it will add the number with the book's price. So we are writing the general purpose equivalent of that. So the first thing we want to do is get the value returned by folding the rest of this list. So you just pass the combiner and base as it is. Okay, it gets you a value of type U. And what you want to do now is combine that value with this dot first, which is of type T. And that's where that buy function comes in. And so you pass it to combiner. And to it, you pass this dot first. And the second thing you pass is whatever that rest returned you. And so this returns you a U, which represents the combination of everything after U plus U. And so that's what you do. Okay. So this is the cons case. The empty case will return whatever it is supposed to be before you start combining stuff. And that's this base right here. So it just returns the base. Okay, questions? See, there's somebody in the chat. Let's see. Luke, is that TUU or TUV? It is TUU because so this is this dot first type of this is, and this are type to be returned. So the buy function is written to take three separate types, but for in the case of fold R, we need something that looks like that. That's why we use the same placeholder letter for the last two, TUU. Okay. Now, before we move on, a last thing about generics. So when you're using a placeholder T, okay, either in the function T, predicate T, buy function, so whatever that generic parameter is, Java places a restriction over that T. And the restriction is that that T can only be something that is not a primitive type. In other words, we could use that iList class to create lists of arbitrary things, but we could not say iList int or iList boolean. Okay, so that seems like a big limitation. However, Java also provides what we call these wrapper classes. These are the class equivalents of all the primitive data types. And so for the primitive, for each primitive type, there is a corresponding class type. Okay, and so for int, we have integer. The class convention uppercase begins with an uppercase. For the double, we have a double. For the Boolean, we have a Boolean. Okay, so if you want to create a list of integer numbers, instead of creating an I list of int, you create an I list of integer. And so now you can have an integer, now you can have a list of numbers. Okay? All right, so once again, let's kind of take a step back and see what we did. We learned about generic classes, and it's okay if you can't read it. I just wanted to capture a 32,000 feet view. This was about abstracting based on type. And what this allowed us to do is, in classes that only differed by the type of data that they dealt, we could write it one time using one or more generic parameters. And that allowed us to write data structures such as a list. That could be a list of anything we want. Okay? The one thing we did have to do was, of all the specific list type methods that we have seen thus far, we needed to conceptually generalize them so that they could apply to lists of any kind. Some of them were simple enough. For example, counting the number of books simply became the length of a list. Neither count nor length really depended on what the list stored, so it was fine. But things like total price, it applies only if the list contains a book or something that has a price. Okay? And therefore, while kind of elevating it to its general purpose equivalent, we instead came up with the three sort of bread and butter higher order functions. The filter, which takes in a predicate, then the map that takes in a function object, and finally the fold R that takes in a by function. Okay? So you're already partly used to this, but the way you can use IList now for creating lists that you want is whatever you want, whatever specific operation you would like to do on your specific list, you must think of it in terms of map, filter, or fold, or perhaps a combination of them. Okay? This is not always possible, of course, but for a lot of cases it is possible, which means there is a lot of benefit to creating one generic type here and then have it be used to and then use it for storing lists of different types. Okay, so let's take up that challenge. So far, there's nothing here that we've seen that will not apply to any of the lists that we have seen so far this semester. So let's pick on creating an IList of shapes. Okay, so why am I creating an IList of shapes? What is new here? Sorry, I shape. What is new here is that this happens to be a union type. Okay, so what? That's fine. We wanted a list of shapes. We could create it. We could create it as always. And now let's say we wanted to convert this list of shapes into a corresponding list of areas of separation. So if you recall, in the iShape class, we wrote in the iShape interface, we had a method called area. Okay? Let's pretend for now that that method did not exist there. Okay, great. So if it did not exist there, we know how to compute the area of a shape. Okay, and so to convert this IList of iShape into an IList of areas that we know is a double, I want this list to contain the areas of the respective shapes in that original IList of shapes. How can I do this? What method or methods can I use to get this list, area list, from that list, S list? Yes. We could use a map such that the area of the first shape becomes the first thing in the IList of doubles. Okay, you can visualize it sort of like this. Here are all my shapes. S1, S2, S3, S4. And here is the list of areas of those shapes. Okay, and roughly the area of this shape is this, the area of this shape is this, and so on and so forth. So this seems tailor-made as a map operation. Okay, so how might we do this? We might want to say slist dot map. Okay, and right here for the map, we need to provide a function object. And what does that function object look like? You look at your map, that was the signature for it. It takes in a function object that has a function in it that takes in one thing, which in our context would be an I shape, and returns one thing, which in our context would be a double. So we need an I shape to double. Okay? And so we used ifunc here, but now that we know the function interface exists, let's use that. And so I would have something here, and that thing is going to be a function that goes from an I shape to a double. Okay, so that's the plan. So all we have to do is write a class that implements that interface, implement the apply method in it, and then create an object of that class and pass it to. But when we are trying to create such an object, that's when we start having some trouble. Here's how. We can write a class shape to area that implements function of I shape to a double. Okay, and therefore what we must do in here is implement a method that looks like this. Returns a double, and then I shape S. Now, remember what I said in the beginning. We are assuming that the I shape interface doesn't have a method that gives us this. There is no area method yet. Okay? You might say, well, that's an unrealistic assumption because we already wrote such a method. And to that, I would say, okay, fine. Then let's think about getting a list of perimeters from a list of shapes. We didn't write the perimeter method. And so we are going to eventually want to write a function object like this. Okay? You see the problem immediately. What I'm given is an I shape. I know how to compute the area of a shape, but the way I compute the area of a shape depends on what that shape is. If it's a circle, it's pi times r squared. If it's a rectangle, it's width times height, and so on and so forth. To get those fields, radius or width or height, I need specific kinds of shapes. And I don't have that here. I have an I shape. Okay? So at this point, we could do what our gut tells us to do, which is, well, let's find out what kind of a shape it is. And if it is a circle, then we cast it to a circle, and lo and behold, we have access to all its fields then, or a rectangle or a square. So that brings us back to using instance of to know the type, which we know is not a good idea. We saw that kind of break on us the moment we started using inheritance with the sameness lecture. Okay? And in any case, that's not a good way to go. We've been saying all semester, anytime you feel like asking what the type of an object is, stop and somehow try to use dynamic distress for this. Okay? And so what do? We don't have an I shape here, and we don't want to use instance of or resort to casting. Okay? So what was the solution last time when we had this? We wanted to avoid using instance of, and yet we had an argument, yet we had a function like this. So this is kind of similar to the sameness method that we had. That one worked on two I shapes. So this one is arguably a little easier. But think about what approach we took when the same shape method that had the instance of turned out to be wrong. How did we design it then? Yes, in some fashion, you're right, double dispatch, but we didn't get there immediately. What was our first step out of that problem? Yes? We delegated something to the I-shape class. Okay? So we call a method in the I-shape class. My problem here is that I don't have a method called parameter in the I-shape class. Remember, it was a step that we took that at the time we took, it seemed kind of weird, but then eventually we managed to connect it back through double dispatch. But what were the kinds of methods we wrote that kind of got us away from this problem? Casting, yes, in order to see if the cast would work or not, we would need to use instance of. And so that's what we are trying to avoid. Trying to avoid using instance of. Yes?
We wrote smaller functions for each I shape.
Good, yes. So we said at the time, well, our problem is that we don't know what kind of shape has been passed to us. So what if we temporarily ignore that problem? And we said, what if we knew exactly the shape that was passed to us? Okay, so let's take that approach here only for the reason that it seemed to work for us last time. Okay, so I'm going to put a pin on this for some time, and I'm going to design one that had sort of a method that looked like this. Okay, you may recall that this is similar to the same circle method that we wrote. And our insight there was that let's make the problem go away of we don't know what kind of a shape has been passed to us. If a method is like this, then we know exactly the kind of shape that is passed to us. Okay, and there are three kinds of shapes. So I'm going to have three versions of this. Apply rectangle to the rectangle class and apply square that takes in a square class. Okay, so instead of having one apply, we wanted three applies, one for each specific time. Okay, so because we would like this, let's make this into an interface. Shape to area. Okay, so the way I would implement it, class the I shape to area. So shape area. Having a bit of writer's block, so I will choose that horrendous name, shape area applier, which will implement I shape to area. Okay, so let me implement just one of them. We know how to implement the others. So given a circle, this method would return the area of the circle. So that would be math.py times c.radius times c.radius. And then other methods would be implemented similar to that. Okay? So far, this is going the same way as the sameness lecture. Remember, our ultimate aim is to get here. We're not there yet. We need a function object like that so that we can map a list of I shapes. So let's keep our eye on that ball. But we have this. Our next problem is, okay, now we have three versions of this apply method that work for the kind of shape. We don't know how to choose which one to call. So this is where double dispatch came in the sameness lecture. We made the shape choose which one it was. How did we do that? We wrote a version of this inside every shape. And then in the in the same shape method, we flipped it over and said, well, I know that one of the objects I have is a circle. So the only method that makes sense here is to call same circle. You remember that? So we use sort of the object that we were in, saying we know this. We don't know what the other shape is, but we know this. And that allowed us to choose which one of the three same circle, same rectangle, same square to call. Okay? So the problem here is a little bit different because we don't have two shapes. We have only one. Okay? And so we need to write some version of a same shape inside every shape that is going to choose this for us. Okay? And therefore, I will add in the interface I shape. This already existed, but I'm going to have a version of the same shape. I'm going to say, okay, this should return me a double. Applied to, and I gave it an object of this I shape to area. So why are we doing this? Because we want the shape. So make the shape choose which apply to call. So we're going to make the shape choose which apply X to call. How are we going to do that? By implementing this method. If we implemented it in the circle class, so let me just do shorthand. In the circle class, we would have applied to. And now my job here is to choose one of those three methods in F. So which method should I call? Well, this is a circle. So if I want one of the applies to be applied to this shape, well, this shape is a circle. So the only one that makes sense is say F dot apply circle. And then whatever it returns, I return. Okay. Let me write one more just so we know. We are in the rectangle class, so we can say apply rectangle. This. And similarly for the square. All right. So if you feel kind of lost in the weeds with everything that we just did in the last 10 minutes, let's review what we did. So first, we said, well, we'd really like to do this. We'd like to map. And for that, we need a function object that takes in an I shape. We attempted to write one, and there we ran into the problem because depending on what I shape is given to us, we want to do different things. Okay? And therefore, we took inspiration from the last time we ran into this problem, which was the sameness lecture. We didn't know what kind of a shape was passed to us. And so we said, let's temporarily make the problem easier. What if I knew exactly what shape was passed to me? Then the problem would go away because since I know what shape was passed to me, I know exactly what fields I can access, and I know exactly how to compute whatever is supposed to be returned. And so I came up with this interface, one for every type of shape. Okay? And so you might think of this as similar to same circle, same rectangle, etc. That approach, although weird, helped us out because it removed any need to use an instance of to find out what shape was passed to us. It tells us what shape is passed to us. And so given that, here's how we can here's how we can implement this interface. Since we are computing area, that's how we would compute it for a circle. And similarly for rectangle, similarly for square. Okay? Now the problem is we need to somehow choose between these three. So you're given a shape, and we have to know for this shape, which one of these three methods should I call? That's the problem I'm trying to solve. Okay? And so I give ownership of that operation, of that decision to the shape itself. I say shape, choose which one of these three you would like to call upon yourself. And so the circle said, okay, I'm a circle, so I'm going to call the circle one. And the rectangle one said, okay, I'm a rectangle, so I'm going to call the rectangle. So we make the shape choose. Okay? So just to put things in perspective, where has this gotten us? We have just implemented an interface and a class that computes the area of the shape. Okay? As I said, we have temporarily ignored the fact that there was a rectangle, there was an area method in the shape. Okay? But just to compare the two, if we wanted to compute the area, so I shape S is mu square, I shape C is a new circle, and so on. Okay? So to compute the area before, before means there was an area method. How would we do this? We would say t.check expect s.area with something. T.check inexact actually. C dot area. Okay, that is how we would find out the area of shape before, when there was an area method. Okay, with this new alternate design that we had, assuming that the area method was not there in the I shape. Now, when there is no area in I shape, how would we do the same thing? We would say C dot or S dot, and we would call this method right here applied to. First, let me create such a method. I shape to area. New. What was it? What was the horrible name I picked? Shape area applier. So I would first create an object of this class. And then I would say, hey, shape. Applied to. I want to apply this calculator to the shape. And same for the circle. Okay, so this was before. The two check-in exacts were before, how to compute the area of shape. The latter two check-in exact are how to complete the exact same operation, but this time without calling the area method, instead going through these classes that we discussed. Okay, so Ivan, I'm going to get to your question in 5 seconds. Let's just quickly go through how this works. So I create the I shape to area method. No problem there. Here, I'm saying S dot applied to. All right, so which applied to will it go there? Because this is implemented in all 3 shapes. S is of type square, so it is going to go to the applied to method of the square class. And the applied to method in the square class that we didn't write was basically going to say F dot apply square this. That would make it to the apply square method here that takes in a square object that will just say S dot width times S dot height. Okay, thus computing and returning the area of the square correctly. Going to the second example, C dot applied to. This time dynamic dispatch will take it to the applied to method defined inside the circle class. That is going to call the apply circle method of this. Okay, so you see how it worked? We never had to write code that used instance of. Instead, we use dynamic dispatch. All right, Ivan, why is I shape to area an interface? The functions apply circle, apply rectangle, and apply square all only have one possible implementation. It doesn't make sense to abstract over a single function. You're absolutely right. And imagine for a second that I give this a slightly better name than what it is. I called it I shape to, actually I shouldn't have called it I shape to area. Let me change it and call it I shape to double. Okay, and so the area is but one such double. I shape to double. So here I will say I shape to double. And therefore, in my examples here, I will say I shape to double. And then to answer your question, Ivan, I can write another class that implements this interface, I shape to double, because this interface can represent operations on any I shape such that the result of that operation is going to be a double. And so area is one, perimeter is another one. If you just wanted to return some quantity that was based off of the I shape, then I could return that. Okay, so those would be implementations of that interface. And now this interface becomes a little bit more general purpose than it was. Does that answer your question, Ivan? Yes.
What happens in the original apply function you wrote?
Ah, yes. What happened to what we set out to do in the first place, which was the map? Right here. Okay. What happens there? So we have the I shape to double here. What if we created this class, where did it go? Area, shape area applier. So we wanted it, so it has the apply circle, it has the apply rectangle, it has the apply square. What we need is that function object that takes in a shape and gives us back a double. If we write such an implementation, if we now set to write this implementation, we have now empowered that I shape to choose which one of those three methods to call. So if only it had access to the correct I shape to double, it could then say, okay, that shape dot applied to and pass that area, that I shape to double. Okay. So let's sort of overload this class so that it has that method. So public double apply, and it's going to take an I shape. Okay, so exactly the same method that we wanted to design here. Public double apply, public double apply. Okay, and now right here, I can say, hey, shape S, apply myself to you. Because we are in the I shape to double, we are given a shape, and so we can say S dot applied to this, and then whatever it returns becomes my answer. So let me underline that, because that is basically what we are move things a little bit so that it's not quite so cluttered. Okay, second time's the charm. It's my fault. My fingers are too fat. I did this. Yes, my pen is not fat. Right here. Okay. And then this was the method that I just designed. Right here. My problem is that my map will not accept an I shape to double. My map will accept a function object. Okay, but inside here is the actual method that the map is actually going to use. So one way is to make the shape area applier also be a function object. Okay, so right now we are saying shape area applier is a I shape to double. That's what we said implements. What we want to say is shape area applier is a function object. Okay, we can't replace the I shape to double with function because we need it to be I shape to double. It is only because of this that the apply to method that we wrote in the I shape even accepts this object. Fortunately, Java allows us to write an interface, write a class that implements more than one interfaces. And so finally, we have a meaningful use case for them. What we say is a shape area applier is an I shape to double and also a function object. What kind of a function object? An I shape / double. So in this way, you can write a class that implements multiple interfaces. They're not inconsistent. It's just that this class is now has an is-a relationship with more than one interface. And so because we added implements function, this method satisfies that. And because a shape area applier is a function, I can pass an object of shape area applier to that map that I designed, thereby completing my method right here. What I wanted to do was take in an area. And so what I need to do is say new shape area line. And this works perfectly fine because that class implements that interface. All right. So once again, let me tie everything together. Our main aim for today was to be able to map a list of union types. There was nothing about this objective that was new. It was a logical extension of what we did last time. We wrote a map on an IList in Jungle, so the map should work for any IList. In order for the map to work, we need a function object there that goes from whatever the list is made of to whatever the destination list is going to be made of. And so if the source list is made up of an I shape, then I need a function object that converts an I shape to something else. And therefore, we needed to write a function object like that. And because I shape is a union type, we can't just implement one thing there. It could be one of three things. That set us down this road. Let us implement those three things as three separate methods. Take out the problem of not knowing what exactly is possible. Okay, so each one of them could be a regular function object that we designed up till now. When we wrote a map that went from books to names or runners to names, we wrote a method like this. It takes in a runner, gives me back a string. Okay, so you can think of each one of these as basically the kinds of function objects we have been writing. That's all. But because we need three of these, we put them in a new interface, then write an implementation of that interface. Finally, we empower the shape itself to choose which one of these three methods to call. We did that by adding a new method here. Hey, I'm giving you this thing that has three functions. Choose one of them that applies to you. That is basically what I'm saying to the shape. And so if it's a circle, it will choose apply circle. If it's a rectangle, it will choose apply rectangle, and so on and so forth. Okay. And so here's how I might use it. You want to convert any one of those shapes into a double using whatever you just implemented. First, create an object of I shape to double, then pass it to shape. This is literally, you are holding 3 cards in front of somebody and saying, pick one. And then every shape picks the card that applies to it. Okay? So instead, if there were only one function in it, the shape didn't have to choose anything. But this extra wrinkle is added because the object we want to work on is a union pattern. It can be one of several things. If it is one of several things, we can have several implementations. And then there needs to be somebody to choose which of the implementations to use. And so we give that power to the shape itself. Okay, that's how you would use it. To tie the thing together with map, we then said, okay, well, this works fine, but I also need this to implement the function interface so that I can use this as my function object to pass to the map method. And so we wrote one here. So we have access to both the shape that we want to change and the thing that we want to use to change it. And so we say shape, I give you myself. I contain 3 other methods. You choose which one you want to call. And then the shape chooses. Okay? Putting this here up allows us to not only use this object to find the area this way, but also to use this object as a function object so that we can map an entire list of I shapes to a list of areas. Okay? So again, I'll pause here for a minute maybe and give everybody some time to digest what just happened. And then we'll try to talk some more about it. But if you have any questions, I'd be happy to answer them. Yes.
So the class we referenced at the very beginning of the shape area class.
The shape to area class. This one right here?
Yeah.
No. So basically, we don't need that anymore because this class became that. Questions? Caitlin, does shape area applier still need the implementation for apply rectangle and apply square? Yes, it does. So I've kind of shortened it here. Let me say dot, dot, dot. Apply rectangle and apply square. We need all of that because it claims it implements I shape to double. In that case, why did we need the apply I shape S? We didn't need it for this class to work like this. You do not need the apply method if you're just going to use that class like this. Find the area of a shape without actually writing an area method inside the shape. If this was all you wanted to do, you could have stopped without and not written the apply method. But in addition to being able to convert one shape into its area, what I want to do is convert an entire list of shapes into a list of areas. And I already have a method that's empowered to do that, which is the map method. What I'm talking about is an I shape to I list of double. But the map takes in a function object. The way I've written it, it requires an apply method that takes in an I shape and produces a double. So in order for me to use the map, in order for me to use that object that I just wrote, not only to convert one shape at a time, but to convert an entire list into a list of areas, I need that object to also have the apply method. And I did that by making this class implement the function interface. Okay. So which method returns the list of areas? That would be the map method. So we wrote the map method here like this. If you remember, the signature of the map method, as we wrote it last time, was it takes in, you call it on an I list of t, so the t here being I shape. It returns an I list of u for some u, so it will return us an I list of double. And because u is a double and t is a shape, the function object expects is something that goes from I shape to double. That is exactly what we provided. All right. So a few years ago, when my parents were visiting, I took them sightseeing in New York City. And one of the places we wanted to go was the Freedom Tower, right? So my parents, like me, are lifelong vegetarians. So every time they come to the States and we have to go outside and eat, it creates problems because they're not used to all the cuisines and they're vegetarians. And so I kind of have to look for places when we're going there, okay, where do we eat? So anyway, we went to the Freedom Tower, they enjoyed it. And then on the way back, if you've been to New York, there are these falafel stands near the 9/11 memorial. And so my dad had never had a falafel. He's a more finicky eater than I am. It says a lot. And so I told him, you're gonna like this. I liked it. And so he ate it. He liked it so much that the next day that we were going to be in New York City, we actually made a detour, came near the 9/11 memorial, only to have another falafel sandwich because he liked it so much. We actually detoured there. So this is kind of like that. We wanted to see the Freedom Tower, but on the way there, we found something else that kept us coming back to it, right? So has something like that happened here? What we wanted to do was merely use the map method, okay? But we have created this whole other machinery. So the question is this really useful somewhere else? What if I did not want to use a map at all? Okay. Luke says, why do you do interface I shape to double F, then call apply circle, apply rectangle? Doesn't that defeat the? Why do you do interface I shape to double F? Interface I shape to double F. Where is that? I remember typing something like this, but writing something like this, but where is that? And then call apply circle.
Yeah, I
Well,
think
I have three methods, Luke. Apply circle, apply square, and apply rectangle. I would like the shape to choose which one of these three methods to call so that I don't have to do it. If I have to do it, then I'd have to write code like, hey, is the I shape a circle? If so, call the apply circle. Is I shape an instance of rectangle? If so, call apply rectangle. I don't want to do that. I would want the shape to choose which one it is because the shape knows what it is. Okay, and that's the reason we went through this apply to method in the I shape. Okay, I feel something may have gotten lost in translation when you type that question. So if I did not answer your question, just type it again and I'll try to answer it. Okay, but anyway, look at what we just did. This I shape to double. So we wrote it in this context. We created that interface because we wanted to calculate the area of the shape. But really, that interface can be applied. The I shape to double can be applied to write functions that would convert an I shape to a double. Perimeter is another different example where we could have it. Okay, but generalizing that more, an interface like this could be useful when you are trying to write functions that will convert an I shape into something else. It doesn't have to be an I shape to double. It could be an I shape to something else. Okay. Moreover, this apply to method. I'm giving it an I shape to double. Think of that object as having three functions inside it, because the I shape to double has three functions inside it. Okay? So it's almost as if I have like a basket of tickets and I'm asking you, hey, pick one. Okay? And because your favorite color is red, you're going to pick the red one. I don't know what your favorite color is, but you do. And so you pick up red. And then you can pick up blue, and so on and so forth. Okay? So we have, to generalize this, I can provide the shape with a basket of functions that apply to them. And then each specific kind of shape can pick the thing from the basket that applies to it. Okay? So it is letting these objects visit itself. Okay? So what we have just kind of engineered is a popular design pattern known as the visitor design pattern. Okay? So let's generalize this. This apply to shape this becomes, in general, a shape visitor, I shape visitor. I don't want it to be a shape to specifically double. What I want it to do is say apply circle C. Apply rectangle R. Apply square. So one method per shape. Okay, but I want its return type to be general purpose. So I say, hey, R. These are different methods that work on different shape that all return the same, a single thing of the same type. So I make this more general purpose. Excuse me. Okay. And then I implemented this thing right here, the only method that I added to my shape. This becomes except an I-shaped visitor. That is going to return you something R. And so this method will also return R. And I will make it a general purpose method. Okay. In fact, since I'm going with the visitor analogy, I will change these from apply to visit. Just give it a more direct. Visit a circle and produce an output of type R. Okay. And so a class that will implement that I-shape visitor will be called a visitor on shapes. So what does this give us? You want to compute a method that takes in a shape and converts it to and computes its area. Great. Option number one, add a method called area in the I-shape interface and implement it. Option number two, don't add anything in the I-shape. Do not change any of the classes that implement it. Instead, implement a class, write a class that implements the I-shape visitor interface. And the R becomes a double because what you would like to produce is a double. You want to write perimeter. Great. Option number one, write a new perimeter method in the I-shape interface, implement it in all the classes. Option number two, don't change the I-shape interface. Do not change the circle, rectangle, and square class. Instead, write a brand new implementation of the I-shape visitor, the R being double. And then when you implement these three methods inside it, you would just take in the circle and return 2 times 5 times R, which is the perimeter. Okay? You want to take in an I-shape and then create an I-shape the corresponding I shape that's twice as big. Okay, option number one, write a method called grow in the I shape interface. Implement it around the classes. Option number two, do not write it in the I shape classes. Do not change any of the shape classes. Write a third class that implements the I shape visitor. This time it returns you an I shape, the grown version of this. And so apply, visit circle is going to return a circle twice the area. Visit square going to return a square twice the area. So you see what I'm doing? This gives me an option to define more and more and more operations on I shapes without every time trying to add that method into the I shape interface itself. So this is very useful when you're defining a union type such that you know what specific types there are, but you don't know how many different kinds of operations you're going to imagine on this. And so when you face such a situation, you can avoid repeatedly adding methods into that interface by just using a visitor pattern. So it allows you to write an arbitrary number of operations on union types without actually changing the interface or the classes for those union types. Okay, so that was the unexpected discovery. That was the falafel sandwich we just found. Okay, yes, it can do map, but even if we did not have to use map, the visitor design pattern, this entire idea has a lot of applications. You can think of the assignment you're working on right now. It's a binary search tree. I can assure you there are a lot more other things that you can do on binary search trees than what you're doing in assignment 6. So you could keep adding those methods there, or you could create a visitor on binary search trees, have to apply to empty, or apply to node, apply to leaf, or for a list, apply to cons, apply to empty, and then stop writing all these methods. Okay. So that's the visitor pattern, and that's where I'll stop. If you have any questions, let me know. Otherwise, I will see you on Wednesday.